Okay, well, thank you very much, Roy and Leon, for inviting me to the Oxford University Scientific Society. And thanks all for coming out. So what I'm going to be talking about today is crowdfunding fusion, focus fusion as a short route to fusion power. Now, let me just start with sort of a question. Well, let me start with the overview of what I'm going to say tonight. We're going to start with the question, which is, what would happen if we had available a source of cheap, clean, and unlimited energy? Then I'm going to say, why should we crowdfund such a source of energy? And then get right into the science, which is, how can it be so small and cheap? How does it work? Where are we in getting to fusion power? And how do we get there? So let's start with that question. What if we could develop, in the next 5 years, a source of energy that came in 5 megawatt packages that was 10 times cheaper than anything we have today, clean, safe, and non-polluting? Just sort of think about that. Imagine what would that be like. Well, first of all, we're spending $5 trillion a year right now on energy, mainly on petroleum. So if that $5 trillion was not going to energy, we'd have a 17% increase in the real income of everyone in the developed sector. In the developing sector, where $1.03 goes to energy, you'd have a 44% increase in real income. Gigantic increase. Not only that, that $5 trillion would be available. It wouldn't automatically, but it would be available to do other things. Potentially, that $5 trillion a year could produce 150 million new jobs worldwide, doing things like rebuilding the infrastructure, building schools, hospitals, providing clean water. One of my favorite infrastructure projects, which was actually proposed 40 years ago, was building a high-speed, hypervelocity magnetic levitation trains in evacuated tubes. Theoretically, such a system could get you anywhere in the world in 2 hours. Which is a lot better than my transatlantic flight. The environmental benefits would be enormous. We would end 7 million deaths annually due to air pollution, due to burning carbon fuels. We could have total recycling with a plasma torch. The plasma torch is an existing technology that takes any waste material and breaks it down to its elements so they can be completely reused. The problem with that is it needs a very cheap source of electricity. We could use the money to end deforestation. And of course, such an energy source would have no greenhouse gases, no air pollution, no radioactive waste. We wouldn't have any more wars over oil. And because an energy source this cheap would make nuclear fission obsolete, you could just lock up the uranium mines and end nuclear proliferation. If you had a distributed energy source as small as 5 megawatts, that's about enough for 3,000 to 5,000 homes, then you could put the energy source very close to the load. Now, a distributed energy network would be very reliable. You wouldn't have enormous blackouts like we had in the New York and New Jersey metropolitan area with Hurricane Sandy. And you'd be able to rapidly deploy this anywhere in the world without having to wait to build a grid. Well, the question for you is, if we had this ideal energy source, and if it would only take $1 million to prove it was scientifically feasible, a prototype generator developed for $50 million, would you chip in, let's say, 20 or 25 pounds to help make this happen, if you believe this was possible? Hands up. Who would chip in if you believed that was possible? So that's why we're crowdfunding. What we have to do, of course, is convince people it's possible. What we're doing is crowdfunding, which for people who don't know the word is simply raising money through established websites on the internet. And we're on a website called Indiegogo. We started May 6th, and so far we've raised about 1/5 of our goal by June 15th, which is $200,000. Now that's to buy a vital part, which I'll describe later on, these beryllium electrodes. To get all the way to a proof of scientific feasibility will require about $1 million. Most of it is coming from private investment. And to go to an engineering model, a prototype generator, would require about $50 million. Hopefully we get that mostly from the government. So why do we have to crowdfund? Or as one article about us said, does fusion need a bake sale? We think we have this energy source, an ideal distributed energy source, which is a form of fusion. Everybody knows is the power that drives the sun and all the stars. Why, if there are billions going into fusion research right now, why do we need crowdfunding for fusion? Well, the problem is that the international fusion effort is focused on a single type of device, the tokamak, and in fact on a single experiment, the International Thermonuclear Experimental Reactor, or ITER, in France. So it's an extremely narrow program, and we can't get money at the moment from the government. Over 50 scientists internationally have signed a letter asking that this international program be broadened to many different fusion ideas. But so far that hasn't happened. And obviously, because we're still in a research phase, although late in research, it takes a brave investor to invest in what we're doing. We have had 50 or 60 brave investors, but it's not enough. It's basically generating about $500,000 per year. So what we need is something else. And since this technology would benefit everybody in the world, it makes sense to ask everybody to chip in. So that's basically the pitch. Now, the question is this possible? What's the science behind it? Or as some people on the web say, is this science fiction? Now, to begin with, what I'm going to explain involves no new physics. No dark matter or dark energy was destroyed in the making of a focused fusion device. This is using physics like electromagnetism and quantum mechanics that have been established for a century, or in some cases 2 centuries, but hopefully doing it in a fairly clever way. Now, what we're not doing is tokamaks, which is the mainline fusion device. Well, probably what you know about it is it's a huge device. That little guy is for scale. So what they're constructing in France is an enormous machine. The first reason why what we're doing is extremely different is we're using a tiny machine. This machine is called the dense plasma focus, has actually been around as long as the tokamak has. It was invented simultaneously in the US and the Soviet Union in the 60s. But we've made significant improvements in it. The electrodes that are at the heart of this machine, we like to say, you can hold the heart in your hands. So this is Ivy, our CIO, holding it, these electrodes, and you can see basically how tiny they are. The entire machine fits in a small room. This is Focus Fusion 1. This is our experimental device. And you can see this set of electrodes, which in the present version is copper, are sitting in the center of the device. If it was in operation, this whole area would be surrounded by a vacuum chamber. But you can see this is only, if you had a man-sized figure, they would be that tall. This is just a room-sized device. So that's the first reason why it's so much cheaper. It takes enormously less energy. This device runs on stored energy in these capacitors of 100 kilojoules. Now, just to give you scale, the largest existing tokamak, which is here in England, JET, has an input of 10 gigajoules. So it's 100,000 times more energy. So that gives you an idea of why our device is going to be a lot cheaper. The second big difference, and the reason why we can make the device so small, is that we use the natural instabilities of plasma to concentrate the energy. That's a very different approach. Most of my colleagues in fusion, not all, but most, are interested. That's very difficult. And one of the only ways you can do that is by scaling the plasma up so big so the instabilities go slower. That's the whole idea. Now, the reason plasmas are naturally unstable is that if currents are flowing through the plasma, then currents moving in the same direction attract each other. Currents moving in opposing directions repel each other. So that's pretty much a recipe for all sorts of instabilities that makes plasmas very interesting. And in fact, that's why they're called plasmas. The Lev Landau, who popularized that term, related the plasma to a living thing, to plasma in blood. So what we're doing is the opposite direction. We're taking natural instabilities, like those that exist in a solar flare or in quasars, or even on the scale of plasmas, of a spiral galaxy, and scaling them way down to the level of the laboratory. Now, how can we do this? The reason is that with plasmas, there are certain scale invariants, things that don't change for a given phenomena depending on the physical scale. And one of these scale invariants, and these were discovered by Hannes Alfvén, who won the Nobel Prize for his developments in plasma physics, is velocity. And that's very important because that means that things that are very transient in the lab, something that takes microseconds in a device like ours, the plasma focus, you scale them up to a solar flare, they take minutes. You scale them up to a galaxy, they take millions of years. On the largest scale, supercluster of galaxies, these same transient phenomena take hundreds of billions of years, which people might notice is longer than the time since the Big Bang. But that's another subject which we'll get to on Monday in the next lecture for the astronomy department. But the key thing to see here is that these phenomena that we can study in a large scale on the astronomical can also be studied on the small scale, and these same natural phenomena be used to concentrate energy in the laboratory. The key way the energy gets concentrated is in a phenomena called force-free vortex filaments. Now, for those of you familiar with electromagnetism, you know that currents moving in a direction create magnetic fields that are circular around them. Well, if you have a force-free filament, the outer currents produce linear magnetic fields that the inner currents run along. And the inner currents produce circular magnetic fields that the outer current runs along. So that in all cases, the current and the magnetic field are running in the same direction. And that's a minimum energy configuration because nature is always trying to do things in the easiest way. So these filaments naturally form, and they're the first stage of concentrating the energy. So let me try and explain how this device, the dense plasma focus, works. So the device consists of a capacitor bank attached to these small set of electrodes. Now, when the capacitor bank fires, it creates a sheath of electricity which breaks up into these filaments and concentrates itself at the end of the electrode into a single filament. The filament, in another instability, kinks itself up into a plasmoid. It's a little tiny ball, just tens of microns or hundreds of microns across, which heats the plasma up to fusion temperatures, to billions of degrees. A final instability creates beams of electrons and ions that carry the energy away. We've observed this many, many times in the laboratory, and there are about 40 other groups around the world that are working on the dense plasma focus. Now, even though we've been doing this for a long time, we really haven't gotten the sort of press the tokamak has. Before this lecture, let me ask, how many people here have heard of the dense plasma focus device? Okay, so most people, many people in fusion, have not heard of this device. But as I say, we've got an enormous amount of experimental data on this. And the plasmoids we can actually see. This is a visible light photograph taken with an ICCD camera with an exposure time of only 1/5 billionth of a second, about 8 nanoseconds after the pinch, which is the time at which those currents we saw in the animation come together. So this is the plasmoid forming. This is the heart of the plasmoid, that little kinky thing. And to give you scale, this whole picture is 1 centimeter wide. So this plasmoid is about 1/5 of a millimeter in radius. So these things really exist. And the neat thing about them is that they are confined by their own magnetic field. The magnetic field in this plasmoid is something of the order of 80 million Gauss, about over 100 million times the magnetic field of the Earth. This is at a level that's already beyond what any human-created magnet, physical magnet, could produce. But these magnetic fields that confine the plasma are created by the plasma itself, by the currents flowing through it. So the first key reason we can make this so small is because we're using the instabilities rather than fighting them. The second key reason is the fuel that we intend to use, which is aneutronic fuel. Now, aneutronic fuels produce no neutrons. The mainstream fusion effort is mainly looking at a fuel which consists of deuterium and tritium. These are 2 isotopes of ordinary hydrogen, tritium being radioactive. When these combine, you get all the energy off in the form of a neutron. The fuel we're using, hydrogen and boron, is a completely different reaction because when these elements react, there are no neutrons formed. Let me just show you what happens. So the proton and the boron combine briefly to make a carbon nucleus. But the carbon nucleus has too much energy to stay together. So it breaks up into 3 helium nuclei, which are also called alpha particles. So the important thing is twofold. One is you have no neutrons, which means you don't induce radioactivity. You don't have any radioactive waste. And the second thing is you can get the energy out directly. I'll explain exactly how. But the energy comes out mainly in the form of an ion beam. An ion beam is moving electric charges, and moving electric charges are electricity. So we can get the energy out essentially with a high-tech transformer, which is enormously cheaper than taking energy, whatever source, using it to boil water, to produce steam, to run a turbine, to run a generator, which is the way we've been doing it since Edison, which is very expensive. So this is basically the way we're going to get the energy out of the device. The main part of the energy will come out in the form of an ion beam. We've observed these ion beams. We know how powerful they are because we can measure them. The ion beam would go into what's symbolized by this coil, which is basically an induction transformer. Induction transformer is the basis of all of our electric motors. It uses a changing electric field to produce a changing magnetic field, which produces a changing electric field in a circuit. So we get the energy out and put it directly into a circuit. The second source of energy is a burst of X-rays, because this is very hot plasma and produces a lot of X-ray radiation. The X-ray radiation goes into this onion-shaped device, which is a photoelectric device, right, working on the same principle as normal photoelectric conversion. But because of the high energy involved, it involves many thousands of layers of metal to capture 80% of the energy involved. Now, this whole device, which we've designed but not yet, which would have to wait until the engineering phase to build, this is going to be a few feet across. So the entire device will still fit in a small room and firing in a pulsed way about 200 times a second, about as rapidly as your car engine fires its spark plugs, would produce approximately 5 megawatts of energy, of power. It would be safe enough to be located in neighborhoods. No neutrons from the main reaction, no high energy neutrons at all. There's a secondary reaction so that about 1/500th of the energy comes out in the form of low energy neutrons. But they're not high enough energy to transform the material of the reactor into radioactive waste. That is, waste that's dangerous to humans or other organisms. The radioactivity, the short-lived radioactivity that is produced in the process, is so short-lived that 9 hours after this device was turned off, you could enter and service it without any protection whatsoever. Radiation would be at the background level. And, of course, no dangerous waste products. The waste material is helium, which is useful, and no greenhouse gases, since this is a process that derives its energy from the nucleus. Now, to get a little bit more into the physics for the physicists here, why have people not looked at this fuel very much? The main reason is because they've been concerned about the X-rays cooling the plasma. We're trying to heat this plasma up, and we've succeeded in heating it up to billions of degrees. As you make the plasma denser, it radiates with these X-rays more efficiently. And the X-ray emission increases as the atomic charge, Z squared. Well, boron has an atomic charge of 5. So it's 25 times more effective in radiating X-rays than deuterium or tritium. So this was a big worry. Well, how do we avoid this? And this gets into the heaviest physics I'll get into tonight. We use something called the quantum magnetic field effect. Now, to understand this effect, I have to start with the fact that in any magnetic field, electrons or other charged particles are forced to rotate, to revolve around the field lines in little circles, like in this illustration. if an electron is hit by an ion, or engages in a collision with an ion, then it's forced into a higher orbit. Now, again, some of this is a little counterintuitive, but it's well-established electromagnetism. When two particles that are charged collide, they don't transfer energy in the direction of their motion. They transfer it perpendicular to that motion. Now, that in a way makes sense. I call it the pedestrian effect. In Manhattan, if you're walking along a crowded sidewalk, and I'm sure this is true in downtown London, you're always avoiding people. You're not bumping into them and being forced back. You move to the side. Well, electrons and ions act in the same way. When they engage in collisions, they move to the side. Now, where does the quantum effect come in? The quantum effect comes in if you have an extremely powerful magnetic field, billions of times the magnetic field of the Earth, then the amount of angular momentum that's transferred, you have to take into account that angular momentum is not continuous. It goes in jumps, which is defined, the size of the jumps is defined by Planck's constant, which is in units of angular momentum. So if you have a very strong magnetic field, the amount of momentum that has to be transferred to make the jump to the next quantum level gets bigger and bigger. And at a certain point, the ions, even though they're very hot, don't have the momentum to push the electrons into the next level. So what that means is that the efficiency of the ions in heating the electrons becomes very low. And because of this effect, and because of the one-sided way it affects the ions and not the electrons, you can reduce the temperature of the electrons so they're 20 times lower than the temperature of the ions. And since the amount of X-rays goes as the square root of the temperature, you can have a reduction of X-ray emission by a factor of 4. Now, that may not seem like a big factor, but what it means is that there becomes a big gap between the amount of fusion energy you're producing and the amount of X-rays you're emitting. And that gap allows the fusion reactions to heat the fuel up without limit, which is what we call ignition. So that allows the fuel to get hot and stay hot for as long as the little plasmoid is confined. The catch is you have to have these enormous fields of more than 3 gigagauss. So that's the theory. I hope it makes a little sense. That's how we can have a very small device working very efficiently. Well, where are we at getting this device? To get to fusion, you need high temperature, confined for a definite confinement time at a definite density. And you have to transfer the energy efficiently to the plasmoid. So we've gotten essentially 3 out of 4. We have proven and published in peer-reviewed journals that we can get 1.8 billion degrees. That's 200 times hotter than the sun. And we can confine it not very long, for 20 nanoseconds, but it's longer than we need. The energy transfer to the plasmoid is about 50% of the total energy. That's very close to the approximately 100% that we need. Where we are not yet there is density. We need a factor of about 10,000. Now again, for the physicists in the audience, right now we have about 10 to the 20th ions per cubic centimeter, and we have to go to 10 to the 24th, which is approximately solid density. But we think we know how to get there. How do we know, people always ask, well, how can you measure a temperature of 1.8 billion degrees? Obviously, we don't have such thermometers. But we can use the neutrons as thermometers. Right now, we're not using hydrogen-boron. We're using deuterium as a fuel. The reason why is first because it's very cheap, it's not radioactive, and there's an enormous database for deuterium. Second of all, it's good that deuterium produces neutrons from an experimental standpoint, because the neutrons are our thermometers. What happens is, when a neutron is produced by a nuclear reaction, it carries away the energy of that reaction, which is fixed, and a variable energy that's based on how much energy it got from the collision. So its velocity is a telltale sign of what the velocity of the ions are, and therefore what is the temperature. Well, we can measure this velocity because we have detectors that are at different distances from the source. One's 11 meters away and the other's 17. So we can see when the neutrons arrive and what's their velocity. The velocity spread gives us a direct measure of their temperature. So what you have here is the energy of the neutrons as determined by the far time of flight, the further detector, and by the near time of flight for a single shot. And from the width of these curves, doing just a small amount of algebra, we can determine the temperature, which is 160 kiloelectron volts, which is the equivalent of 1.8 billion degrees Celsius, or Kelvin. People were actually pretty interested when we published this result. We published it back in 2012 in Physics of Plasmas, which is the leading journal in our field, and we were pleased the next year to discover this was actually the most read, the most downloaded article. And we know from conferences people are really interested in discussing this because it was very hard proof that these temperatures are actually confined to a small spherical area. One common question we get is, why does it get so hot? And we've done some theoretical work on this, which has been presented at conferences and not yet published, but we're quite confident. The basic mechanism, which was first proposed by Professor Haynes and others, is viscous heating. And the idea of viscous heating is that the ordered motion caused by the contraction of the plasmoid is converted to random motion, to heat. And the easiest way to think of this is to think of traffic. When you have traffic moving on the highway, you're having the cars moving in the east direction and cars moving in the west direction. They're moving at high velocity, but their velocity relative to one another in the same lane is very low. So what you would call the thermal velocity is high. Now, if you imagine some catastrophic error that directs the eastbound lane and the westbound lane in the same direction, well, in traffic sense, you get a tragedy. But in fusion sense, we want collisions. It's a good thing to have collisions. But all of a sudden, all that ordered motion would be changed into chaotic or random motion. That's what viscous heating is doing. At higher densities, we'll also have another effect, which is the electron beam will set off waves in the plasmoid, which will also heat it up. So we've shown analytically that we can actually predict temperatures very similar to those that we obtained in experiment. Now, to give you a comparison of where we are relative to other people in fusion, this is the amount of fusion energy that's produced in experiments for every 1,000 joules that's put into the entire machine. Remember, I was saying, for these jet experiments for the tokamak, you're talking about tens of gigajoules. For us, we're talking about tens of kilojoules. So if you use deuterium-tritium fuel, which is a very rapid burning fuel, the biggest tokamak experiment got out 2.2 joules for every 1,000 joules put in. We don't use deuterium tritium. I was just asked at dinner time why not. The main reason is we don't want a radioactive device. So, but our colleagues in Russia at Sarov have built a similar machine, another DPF. They get out 0.2 joules. Now, by comparison to that, NIF, the giant laser in Livermore, California, they got out in their most recent experiments 0.03 joules. So the DPF is already doing better than this $5 billion laser experiment. If you look at deuterium reactions, pure deuterium, which is a lot less reactive, we're getting about we're getting about 2.5 millijoules out. Now that doesn't sound like much, and it's far from what we need, but it's about a quarter of what the 1,000 times more expensive tokamak experiment did. And it's actually better than our colleagues in Russia have done. So that gives you an idea of the comparison between our little experiment and these much larger experiments. Now, why aren't we there? Why haven't we already announced getting our goal, which is getting more energy out than we put in? That's a key point, and it gets really into why we're raising money. If you plot the fusion yield of this device, the dense plasma focus, against the neutron yield against the current, and these are log scales, then until the machine gets quite large, you have a very nice scaling relationship, which is the energy output goes as the fourth power of the current. That's important because the energy input goes as the square of the current, roughly. So the energy output is going much faster up than the energy input. The problem is when you reach about 10 to the 12th neutrons, which is about 1 joule of energy, you get a plateau. The yield stops going up. Now, we experienced the same effect in our device. We were going up actually faster than our colleagues. This is our results. But we reached the same plateau. So we worried a lot about that for about 1.5 years. And we discovered, and we've pretty much demonstrated, although again, our publication hasn't caught up with us, that there's a very simple problem here, which might be familiar to anybody who is working in the fusion fuel, and that's impurities. What's happening is we don't have a pure deuterium plasma. The electrodes are being vaporized by the current, and this heavy metal vapor, copper vapor, is basically lousing up our experiment. This is a picture of an electrode after being exposed to several hundred shots. Now, in our device, we can fire maybe 10 or 15 shots a day. I'll explain what you're looking at. This part of the electrode has been cleaned up superficially with a little abrasive, and it shows the color of the electrode, which is silver, because this copper electrode has a very thin, about 40 micron thick coating of silver on it. That's to prevent oxidation and things that we don't want. This is the area that is very close to the insulator, where the current discharge that we saw in the animation starts. And you can see the silver has been eaten away, vaporized, and there's actually a crevice cut into the copper. And if you look over here, where we haven't cleaned up, you can see the copper color is redeposited here. So you're getting vaporization, and much of the copper is being carried into the plasma. And this is quite a bit. we calculated how much it was, and by mass, about a third of the plasma is copper, about 2/3 is deuterium. We did very careful measurements based on how rapidly the sheath moves down the electrodes, because the heavier the sheath is, the slower it will move. So we can use that to determine for each shot how fast it was moving and what the ratio of impurity to deuterium mass was. And basically, you can see most of the shots are somewhere around 50%. So there's 50% as much copper mass as deuterium mass, or about a third of the whole mass. Well, how does that impact our results? It impacts it in a very big way in terms of density. We're trying to compress the plasma through its own magnetic fields. So this has to be a symmetric compression. Well, if a third of the mass is these impurities are entering essentially in a random way where you're vaporizing more of the electrodes, that makes for a very uneven compression. So you can't possibly get the very high densities that you want, and that these smaller experiments that had purer plasmas did achieve. The more complicated reason is that it makes it harder for these filaments to exist, because the filaments are the first stage of compression, a very vital stage. The magnetization, the degree to which they're controlled by magnetic fields, is dependent on whether the orbital velocity around the magnetic lines is faster than the collision velocity. If in one orbit they encounter a collision, then they're not really bound to these magnetic field lines. So the magnetic filaments are not very strong. And this collision rate goes up as the fourth power of the atomic charge. So when you have copper, which has 29 charges getting into the plasma, it has a huge effect and disrupts the filaments. And we actually observed that. This is from a smaller experiment done years ago in the 70s at at Stevens Institute in Hoboken. And this was done by my mentor in this field, which was Winston Bostick, and his colleague Vittorio Nardi. And the direction we're looking here is straight down the electrode. So these are the filaments that I'm talking about coming out of the electrode and becoming concentrated in the pinch. Now, this is a side view of the same thing, and you see the filaments being concentrated in the pinch. Now, when we looked at our machine, where we had clear evidence that the filaments existed early in the shot, when we looked and took photographs later in the shot, this is what we saw. The sheath is completely smooth. This is a sector of the sheath. Our field of view wasn't completely central. So you can see there's not a hint of the filaments. So we knew that the impurities were destroying the filaments. Why does this get worse at higher currents? Well, first of all, you get arcing. Arcing is when you have two metal pieces joined together and a spark jumps across them. Or you have what's called contact resistance. And the contact resistance causes the metal to heat up so much that it vaporizes. The more the current is concentrated, the greater the current per square centimeter, the more the heat, and therefore the more the arcing. So the small machines that fit that curve so nicely didn't have the arcing because they didn't get hot enough. Second of all, this magnetization disruption becomes much easier. Magnetization depends on the ratio of the B field, the magnetic field, which ties the ions and electrons tightly into the filaments, and N, the density, which causes the collisions that break them away from the filaments. When you get higher currents, because this ratio, which is tied up with the velocity, is the same, this ratio declines with the higher currents. So it becomes easier for the filaments to disrupt at higher currents. So that's why it wasn't visible at lower currents, but the bigger machines got the impurities. That caused the plateau. Well, how do we get rid of the impurities? We've done a lot of thinking, and we're pretty sure we're on the right track. First of all, we get rid of the arcing with a monolithic electrode. Monolithic means there's one piece of metal which is attached to the circuit outside of the vacuum chamber. Now that, first of all, spreads out the current contact so you don't get arcing at all. And second of all, if you do get arcing, it's outside the vacuum chamber, so it doesn't matter. Second of all, we change the material from copper to tungsten. Tungsten has an extremely high vaporization point. It's a very tough material, so it's very hard to vaporize it under any conditions. This is the tungsten anode we received a few weeks ago, and we're going to have a tungsten cathode as well, which looks sort of like this. This is a drawing. This is being machined in New Jersey right now as we speak, and we should get it by the end of next month. Again, it's pretty massive because it's attached outside of the vacuum chamber, but it's still relatively small. This dimension out here is just 30 centimeters. So we're pretty confident, we're very confident, in fact, that the impurity level will go down by a factor of about 50, and we expect our yield, our density, to go up by approximately the same amount. It's not totally linear, but we should be able to reach the theoretical densities that we expect and that other people have observed with this next set of experiments. And that will drive our yield up by a similar amount, maybe a factor of 100. If we achieve this, the next step in density to cover this 20,000 or this 10,000 gap that we talked about would be to increase the current to full power. At full power, we expect to go up from our present 1.5 megamps to almost 3 megamps, and that'll increase the density tenfold. We get a 20-fold benefit in density simply from having the heavier elements. The process works out in such a way, and this was theoretically predicted in my work back in the 80s, that the heavier elements have a greater compression ratio. So for the same starting density, we get about 20 times bigger finish density. So if you put those numbers together, that's how, over the course of a year to 18 months, we expect to close that 10,000 density gap. It sounds like a lot, but in physics experiments, it's not unusual to get these big jumps. At the same time, by compressing the field more and more, by this self-compression of the plasma, we expect to get up to the magnetic fields that's necessary for this quantum effect to prevent the X-ray cooling. So with the filaments, we expect to go from our present 0.08 gigagauss to about 0.6 gigagauss. With full current, we'll about double that, and with the greater compression with hydrogen-boron, PB11, we'll get up to about 10 gigagauss, which is well beyond what we need. Now, that's not the end of the story, because the tungsten electrodes are extremely tough for everything that the machine produces except X-rays. As we get closer and closer to net energy production, the X-rays are going to go up until thousands of joules are being emitted as X-rays. And the unfortunate part is that tungsten, as a heavy metal, is very good at absorbing X-rays. So the X-rays will be absorbed in a very thin layer of tungsten, and that means that the tungsten would start to crack. So we need to replace that with beryllium. Beryllium is the lightest metal. It only has 4 charges, and most of the X-rays would pass through it, and the ones that don't will be spread out. Problem with beryllium is cost. At the moment, the United States government has established, I'm not sure how, a worldwide monopoly on beryllium, and they gave that monopoly to a single company, and we have to buy from that company. Oddly enough, beryllium is quite expensive. So our estimate is, or their estimate is, that the one-off single unit production cost of these beryllium electrodes would be something in the area of $200,000 or $250,000. Since our budget is only about $500,000 a year, that puts a real dent in it. That's what we're crowdfunding for, is that boost in our budget. Now, people ask, well, if we got to break even, what would be the engineering challenges to go beyond that to get to an actual generator? Now, we have a very small staff. I'll get into that again in a moment. So we don't have time to look in depth at the engineering challenges, but we do know what they are. First of all, even with these electrodes, there's a certain minimum amount of erosion that's unavoidable. It's a process called sputtering, which is when the ions smack into the electrode, on occasion, not very often, one of the atoms of the electrode gets bounced off. So there's a physical erosion. Now, that might let the electrode last a few weeks before its shape is significantly distorted. And that might be enough. That probably will be enough, because if we change out the electrodes every few weeks, and we have to shut down the machine for maybe half a day, that's still more than a 90% availability. And that's pretty good compared with our existing energy sources. Second, the anode is going to be heavily heated by X-rays. So that's going to be an upper limit in how fast this machine can fire, because you have to take all of that heat by some coolant, probably compressed helium, out of this very small anode. And we have to worry that the boron is going to simply precipitate out of this very hot gas, because boron is at room temperature solid. So we can't fire it too slowly either. So that's why about 200 times a second is going to be about right. So these are some of the engineering challenges that we're going to have to deal with in the engineering phase, which would take a much bigger staff. The final question I've been asked and I want to deal with before we open it up to questions: why has it taken so long? I mentioned that people have been working on the dense plasma focus for about 40 years. Why aren't we already there if it's such a good machine, it's so cheap? The first, second, and third reasons are money. Even though this machine is very inexpensive, I mean, we built our device for about $500,000. It's totally underfunded. Underfunding has many malignant effects. First of all, you pick your materials on the basis of cost. Somebody asked me, well, why didn't people go to tungsten? Are you the first to discover tungsten was better? No. This was published 20 years ago in the literature, that tungsten was vastly superior to copper. Tungsten is about 10 times more costly than copper. Copper is a very cheap industrial material. So that's why people stayed with copper. They just didn't have the budget to even contemplate going to tungsten and looking at why it would be better. Second of all, there are too few large experiments because of funding. Our device is approximately the third most powerful device in the world. The biggest one is in Warsaw, and the second biggest one is in Las Vegas. And if you have very limited funding, you make a single big machine, and then you're sort of stuck with it. The one in Warsaw is about 30 years old. And when people started to notice this impurity problem, many of them went in the wrong direction. They wanted to spread the current out by simply making the device larger. And the problem with making the device larger, as we pointed out theoretically, is that the magnetic field, the density, all goes down. So your yield is adversely affected. Also, if you've got a large machine, your expenses go up in terms of material. What to us, the tungsten electrodes cost $60,000, to our colleagues in Warsaw, the same electrodes would cost $500,000. And finally, you have enormous understaffing. Most experiments have only a few, 2 or 3 physicists working on them. Warsaw is an exception, they have a dozen. Our staff is extremely tiny. I and Ivy are the full-time staff. Ivy does everything else that is not directly connected with the lab, the website, the computer work. We have Fred Van Russell, who is part-time with us as an electrical engineer. We have Warwick, who is working full-time as a contractor on our simulation. And we're going to have, and we have Bob Fitzgerald, who's out there raising money for us. And in the lab, we're going to have a new person, Tony Ellis, coming on board. That's a ridiculously small staff, even for a device as small as the plasma focus. We could easily have 5 physicists working productively on this. This is all money limited. And 5 physicists don't work just 5 times faster than 1 physicist. We come up with good ideas by talking to each other. So the key problem with this entire plasma focus field has been enormous underfunding, which comes back to the crowdfunding, which I'll end on. We don't expect crowdfunding to substitute for the government funding that really has to be going into devices like the plasma focus and the many other good ideas people have come up with to get to fusion that are other than the giant tokamaks. But crowdfunding can act as a spark, because if we can use crowdfunding to get the money we need for vital parts to get to net energy out, then I think government funding will flow. People will say, these other alternatives are really working. When you look back at what I started with the consequences of getting something that is not just clean, but is cheaper than all other energy sources. And I want to emphasize that, because as far as I know, no other alternative energy source except ours would be many times cheaper than existing energy sources. Then you get rid of the other energy sources. You wipe out oil and gas and coal and all the pollution that they create. You wipe out nuclear fission. They simply become obsolete. Given the enormous impact that this has, it's crazy not to put money into it. This is a research program, so can we guarantee success? No. If we could, it wouldn't be research. But this, we know of nothing, and no physicist has pointed out to us anything that prevents this approach from working. Given the consequences, it seems to me very logical that people should chip in. And if they do, and this is the slogan of our campaign, we will give power to the entire world. As we put it, let's focus fusion, empower the world. Thank you very much for your attention, and we'll be open for questions.